what it looks like is that you have a lattice made out of, okay, maybe they are electrons. We're going to confirm that in a second. So we have a lattice, and we can measure the lattice constant just like you can measure any kind of periodic structure from these images. And then you can ask, is this a lattice made out of single electrons? It turns out that you can do this so here you control the density of electrons in those pictures. On this axis, you measure the distance, which is the lattice constant between what I call those balls in the picture. This seems to confirm for us that indeed what we have done is we have made a crystal made out of electrons that they are just repelling one another, and they just arrange themselves in a hexagonal lattice. Now you look at this picture a little closer, and you say, well, what determines the size of this feature? Is this a single electron? Well, you read the numbers from the experiment. This is 30 nanometers. Okay, electrons are very small. 30 nanometers is a very large number. It's a billionth of a meter or a nanometer, but electron is much, much smaller than 30 nanometers. What are we looking at? It turns out that what you're looking at is basically the quantum uncertainty of where this electron is. It's living inside this crystalline lattice, but it actually is, there is an uncertainty of where it is. And it's actually this sort of region that we see in this instrument is actually telling you about this quantum uncertainty. And the amazing thing about this lattice is that the quantum uncertainty is a very big fraction of the distance between the electrons. This makes it a very unusual lattice structure. This gives you an example of electrons interacting very strongly and making a crystal when they should. And this crystal is just purely made out of repulsion between the electrons. And this particular crystal is sort of the simplest example that you could make of electrons interacting. You might have noticed that I didn't plot any data in this little region in this plot. What happens there? Let's go back to the pictures. So I showed you this picture. I didn't show you what it does all the way. Actually, if you change, these numbers just reflect how you're changing the density of electrons. You change it from some number to a very particular number, which is 0.33333. What happens is as if this crystal of electron has melted. And this melted crystal has made something which doesn't have any features in our experiment, like a fluid. It turns out that this is a very special fluid. And it was discovered actually long ago, about 40 years ago, in different experiments, not microscopy experiment like we are doing here. It was discovered in experiments where you pass an electrical current through this two-dimensional gas of electrons under the same conditions. What are the conditions? Remember, I told you that what the magnetic field does is it creates this narrow range of energies where electrons can live. It turns out that there are some very magic, we call filling, of if you fill this all the way, it behaves one way, but if you fill this a third of the way, it creates a certain kind of quantum fluid, kind of like a superfluid, that has properties which are macroscopically distinct from a metal. Actually, they show quantized behavior measured when you measure its electrical property. So we have this interacting soup of electrons. Interacting soup of electrons can make a crystal. If you just change the number of electrons interacting at some magic number of them per unit area, you have a magnetic field present, electrons create a completely different state. Now the crystal, it looks like a melted crystal, and it has some interesting property. In the last few minutes, let me tell you what's interesting about this. Theoretically, what we believe happens, you make a fluid. It is very unusual. It's kind of like a superfluid. But what's unusual about this particular fluid is that no longer you cannot think about electrons as those balls that I described as sort of the basic, if you like, property of this liquid. Electrons are so entangled with one another, they make a new kind of liquid, which if you add energy to it to excite it, it creates excitations that are not like electrons at all. They actually have a fraction of a charge of an electron. Okay, so first we have a superconductor, which carry resistance with no resistance when you make the sun a superfluid. Here we have a different kind of quantum state in which it has resistance. Actually, the constituent parts that are carrying electricity inside are not electrons anymore. Actually, fractions of an electron. Now, why am I telling you this? The reason is, at the beginning, described to you that in nature there are two kinds of particles: fermions and they're bosons. We talked about the beauty of bosons. Bosons make us that superconductor, and so on. It turns out that how you distinguish these two set of particles is you have to think about, if you and I are the same particle, and if we change places, right, everything should stay the same, right? So there are two ways in which everything can stay the same. We have a description in quantum mechanics. When we talk about these wave functions that we describe, in one case, the wave function can just be the same as it was before. If we are the same, we change places. In terms of fermions, when they change places, there is something happens to the wave function where you get this change of minus sign, which is not that important when you think about the overall properties. When you think about the probability where the particles are, this makes it very different between what fermions do and what bosons do, and this is essentially gives you this social antisocial behavior. It turns out that the particles that are living in this new quantum fluid that I described to you is actually something, particles that are kind of in between, are near fermions, near bosons. Okay, the reason we are interested in these particles is that we can do things with them that are not possible with fermions and bosons. It turns out that one of the special things you can do with them, which is sort of counterintuitive, is that if you took one particle and took it around the other one, it kind of remembers how you did that. It remembers if you went one way, the other way. And if you think about sort of in time, you move these particles around one another inside this fluid, you create something in terms of a quantum state. It kind of looks like you have braided timeline of these particles together. Okay? So what's so special about braiding? Well, you want to undo it, there's only one particular way you have to do it, right? It's gone one way, you have to undo it in a specific way to undo the braiding. What's special about this is you can try to encode information, how you took these particles around one another. If you encode information in this particular way, it has what we call more protection, because in order to undo it, you have to undo it only in a particular fashion. Part of the reason we are interested in these states, in these quantum states, is to try to create the next level of quantum bits. So the whole information technology based on quantum information is about how do you encode information in a quantum system. Remember the superconducting loop? He said the superconductor, you can have the current flow one way, you can have it flow the other way, and then you can encode information in these two states configuration. Here, you can encode information in a completely new way, which is based on exchange of these particles and how they move around one another. In fact, this is not just something academic. Actually, even there is an industrial effort by Microsoft is trying to exactly what I'm talking about, is related sort of ideas where they're trying to sort of use these particles to create kind of quantum bits. All right. So I think what the message I want to leave you with, I've already gone a few minutes over, is that, we have ordinary metals, insulators, even ordinary superconductors, which we understand very well. And they give us our technology and amazing things today. But now we have a whole set of other stuff, other quantum state that comes from the emergent property of many electrons talking with one another, the superconductor being one of them, this exotic fluid being another. And I think that, let me just skip this and go to the end because I've run out of time. And I want to just end by just saying, this is one of the frontiers of quantum mechanics, is trying to understand the emergent behavior of many particles interacting with one another. Materials view very unusual, very amazing opportunities because you can kind of write different rules about how you create states because of, periodic table is very large, many kind of atoms you can put in a crystal, many kind of crystal structures we can make, and the possibilities to kind of look for these exotic state is kind of, at this point, looks like we have a long way to go to exhaust it. With that, I stop and take any questions.
So the question you're asking is kind of deeper than what you're maybe intending to. So let me back it up in a second and say, you can actually detect the fractional charge. There's a guy sitting in the back here who did one of the first experiments to know that the fractional charge is there. And then the question is whether if you have one, is this going to behave, you can make it behave like a particle. You can certainly make it behave like a wave. So people are actually doing experiments now where they're trying to interfere these particles with one another. It's like those pictures I showed schematically. So yes, there would be both. You can treat it like a particle and you can treat it like a wave, just like other exotic particles. For a non-specialist, please explain in short, quick, how is this going to affect our lives? Why is this important to our lives? So I think so let's take a little bit of sort of view about 30, 40 years back. Essentially, all the technology that you use now are based on breakthroughs on trying to understand quantum behavior of materials with quantum mechanics, applying this theory to materials and using it to make transistors, magnetic devices, and so on. And we have reaped the benefit of that, of course, in spades. Yeah, this is my iPhone. But what's gonna come after? We are discovering new phenomena, which the application of some of which are, I try to sort of allude to some of which is still unexplored. So I think that the way this field works is that people don't realize that whenever we make a discovery, actually 5-10 years from that, technology just emerges because it's the stuff you can hold in your hand and you can put it together in devices. And I think that this is kind of the important message, that applying quantum mechanics to understanding materials have just keep being, paying. Of course, I didn't talk about light, which is another part of quantum phenomena that is paid in spades. So the question is, what are these charge imbalance or unbalance come from? Like what happens to where the extra charge come from, and what does it mean for the overall charge of the material? So what happens is that when you tune your conditions to be in this kind of exotic fluid, you have a certain density of electrons. Density of electrons is fixed. Now, what you do is you say, imagine you add energy to the system, try to excite it. It turns out that what gets excited is not an electron that's sort of at a higher energy level. You can't do that. There is a more subtle thing that happens, which is a fractional charge that emerges from many electrons basically being excited. And then the distribution of this fractional charge depends on sort of details of where you are relative to destroying the state. It turns out that as you create more and more of these excitations, you can basically collapse the state where everything disappears and you are back to single electron. The description I have of fractional charge is one of excitation of the system.